In this video, we're going to talk about some specific kind of sequences, namely arithmetic and geometry ones. Let's get started with arithmetic sequence. By definition, an arithmetic sequence, or we might sometimes call progressions, arithmetic progressions, is a linear function from the set of positive integers into the set of real numbers, sending an element x to ax plus b, where a and b are some real numbers. Okay, so we might now ask how to determine terms of the sequence. For example, if you want to compute f1, f2, f3, f4, f5, you only need to evaluate the linear function in each case. So it is very easy to see that this sequence look like a plus b, 2a plus b, 3a plus b, etc. And there are very easy pattern that you can see about this sequence. If you want to get from the first term to the second term, you can add to the first term an amount of a. And similarly, if you add a to the second term, you get the third term. And so on for if you want to pass from the third to the fourth and from the fourth to the fifth. So a is actually the common difference between two successive terms. Well, and this actually characterizes an arithmetic sequence, meaning that a sequence is an arithmetic one if and only if the difference of a term and its preceding one is a constant. It means that, well, whenever you compute the difference between two successive terms, you should get a constant. So for example, giving you a sequence 6, 9, 12, 15, and 18, etc., then actually you can tell that it is an arithmetic sequence since the difference between two successive terms is 3. 9 minus 6 is 3, 12 minus 9 is 3, and so on. So in this case, the first term is a1 equal to 6, and the common difference is 3, which we denote by d equal 3, because d stands for difference, right? It is the initial letter and the word difference. And because of this remark, we know that an arithmetic sequence can be defined recursively by first clarifying the first term, a1, and then after that for an is greater than 1, then you can define an using an minus 1, and the specific formula here is that an is equal to an plus 1, an minus 1 plus d. And from this you see that the difference an minus an plus 1 is always d, which means that d is the common difference in this case. Okay, so giving an arithmetic sequence is equivalent to giving the first term a1 and the common difference d. And from that information, we know that the general formula for the term an should be an plus n minus 1 times d. This can be easily proven using the definition of arithmetic sequence. Recall that an arithmetic sequence is actually a linear function of the form ax plus b. Then you only need to mean a and b in order to get the formula for the n term of the sequence. Now, you know that the common difference is actually the slope of the function, so we know that a should be d. And then because the first term is a1, then you know that f1 is equal to a1. And because you know that a equal d, then if you substitute 1 into the expression ax plus b, then you know that d plus b equal to a1, meaning that b is actually a1 minus d. And now pack them together, you know that an is equal to d times n plus a1 minus d, which is nothing but a1 plus n minus 1 times d. Now, you can actually compute the sum of the first n terms of an arithmetic sequence. This can actually be done using two different ways. The first way is that you compute as n the sum of the first n terms of the arithmetic sequence with the first term a1 and the common difference d is n over 2 times 2a1 plus a minus 1 times d. And an equivalent way of computing this, it should be n over 2 times a1 plus an. So why do we care about the different way of computing the first n terms of arithmetic sequence? Because it depends on whether the information that you are given. So for example, if you are given only the first term and the common difference d, then the first formula should be very easy for you to work with. But however, in case you are given an arithmetic sequence using listing with patterns, then you might possibly know a1, a2, etc. up to an. So in this case, computing the sum of a1 and an should be way much easier than first try to define the determine the common difference. Okay. So before proving this, let's see why these two formulas are actually the same. So from the first formula, if you split a1 into a1 plus a1 and then you regroup a1 with an minus 1 times d, you know that a1 plus an minus 1 times d is actually an. So from this reason, we get the second way of computing as n, which is n over 2 times a1 plus an. Okay, so now because we know that these two values are the same, then we only need to prove that n is equal to the first value, and then we are done. Okay. So Sn is actually the sum of the first n term of the sequence, and you know the formula for each term. So the first term is a1, the second term is a1 plus d, the third term is a1 plus 2 times d, and so on. The n term should be a1 plus n minus 1 times d. Well, you know that here a1 appears n times, so you can regroup a1 and you have n times a1 first, and then after that you have elements involving d, so you have d plus 2d plus etc plus n minus 1 times d. So using summation notation, you know that you can put d as a common factors, and this now becomes d times the summation of k, where k is run from 1 to n minus 1. And you already have the formula to compute this sum, then it should be n times a1 plus d times n minus 1 times n over 2. And well, from this you know that this is actually the first formula that you are given in the statement. Now let's talk about a geometric sequence or geometric progressions. It is actually the function of the form a times r to the x, where a and r are some real numbers, and we require that r should be non-zero. So this actually looks like an exponential functions, but remember that in the definition of exponential function, we require that a should be different from 0 and a should be different from 0 and 1, and moreover r should be positive, right? So in this case, we do not call this an exponential function for that reason, because we only require r to be different from 0. So we can also compute the first several terms of a geometric sequence, which should look like AR, and then a times r squared, a times r cubed, a times r to the 4, a times r to the 5, etc. And so visibly, we see that if you want to pass from the first term to the second term, you have to multiply the first term by a. And from the second term to the third term, if you want to get the third term from the second term, you have to multiply the second term by r, and so on, from third to fourth, from fourth to fifth. And so actually r is the common ratio, meaning that if you take the quotient between an and an minus 1, it is the same number r for any n. So that's why we call this the common ratio. And similar to the situation we have with an arithmetic sequence, we know that a sequence is geometric if and only if the ratio of successive terms is a constant. And this is actually the reason why we required the ratio to be different from 0. Okay. So from this remark, we can actually tell whether a sequence is geometric 1 or not. We can do that simply by computing the ratio of successive terms. And in this case, it is 3. So we can easily deduce that the first term is 2 and the common ratio is 3. And here R stands for ratio. It is the first letter of the word ratio. And also we know that a geometric sequence can be defined recursively by first clarifying the first term a1, and then after that an should be equal to r times an minus 1, because the ratio between an and an minus 1 is always a constant number, which is r, the common ratio. So we know that giving you a geometric sequence is equivalent to giving you the first terms and the common ratio r. And from this we can recover the formula for the geometric sequence as an is equal to a1 times r power n minus 1. This can be proven quite easily because we know that the geometric sequence should have the form like, which is actually like an exponential functions a times b to the x. So by abuse of notation, we just call that exponential function, but keep in mind that it's actually not, because we do not require b to be positive or different from 1. Okay, and a might be 0 too. So because the common ratio is the base, so we know that b equal r, and as f1 is equal to a1, then we have a times r is equal to a1, and giving you that a is equal to a1 over r. Okay. Then from this, you know that an is a1 over r times r to the n, and it should be a1 times r to the n minus 1. So that gives us the formula that we stated before. Now we can also find the sum of the first n terms of a geometric sequence. So suppose now that you have a geometric sequence with the first term a1 and the common ratio r that you require to be not only different from 0 but also different from 1. Then the sum of the first n term of this sequence can be computed using the formula Sn is equal to a1 times 1 minus Rn, r power n, over 1 minus r. So from this formula, you obviously see why we have to require r to be different from 1. We can prove that as follow. Sn is actually the first n terms, and using the formula for general terms, we know that it should be equal to a1 plus a1 times r plus etc. plus a1 times r to the n minus 1. Well, now we will divide this into two parts. We regroup a1 times r plus etc. plus a1 times r to the n minus 1 as a term, and we add it with a1. And because we divide this into two terms, then now we can actually minus the first term by a1 times r to the n, and then we add the same amount to the second terms. But the first term should be a1 times 1 minus r to the n, and the second term now have the common factor r. And when you take the common factor out, then inside the bracket, what you get is actually Sn. So now actually you have an equation including Sn as a variable. Then you can easily solve this to have Sn equal to a1 times 1 minus r to the n over 1 minus r. Okay, so you get the desired formula. And remember, because in this case we require the common ratio to be different from 1, then you might ask the question, what is the sum of the first n term given the common ratios are equal 1? Well, that should be an interesting exercise for you, where a hint for you is that in this case where the common ratio is 1, then this is actually a constant sequence. And we already have a formula for computing the first k term of a constant sequence. Now, example. If you want to find out the summation of the sequence 1 over 2, 1 over 4, 1 over 8, etc., meaning that we have the sequence ak equal to 1 over 2 power k. So in this case, we know that the first term is 1 over 2, and we can easily see that the ratio is 1 over 2, 2, which is different from 0 and 1. And so we have as 10 is equal to an times 1 minus r to the 10 over 1 minus r. And so you just need to substitute 1 over 2 into the expression, because a1 and r are the same and are 1 over 2 in this case. And by easy computation, we know that it is 1 minus 1 over 10, 2 to the 10th. So now we talk about geometric series. Given a geometric sequence with the first term a1 and the common ratio r, then an infinite geometric series is actually an infinite sum of the form a1 plus r plus a1 plus r squared plus etc. So actually what you're doing here is that you take the sum of all the terms of the geometric sequence. Well, this is actually just a symbol. We call this infinite sum a symbol because actually you only define the sum of a finite number of numbers, right? But you never know how to compute the sum of an infinite numbers of real numbers. So remember that it is just actually a symbol, and this is a little bit long, right? Then we use the summation notation to represent this number. That is the summation of a1 times r to the k, where k is running from 1 to infinity. Okay, so keep in mind that up to now we only have that as a symbol. Well, now we can actually say how to compute that symbol in specific case. So if the sum of the first n terms of the geometric sequence approaches a number L as n tend to infinity, meaning that you can compute the limit of Sn, then we say that the infinite geometric series converges to L, and L is called the sum of the infinite geometric series. So actually, now the symbol, the infinite geometric series, can actually be computed by computing the limit of Sn when n approach infinity. When you know that the limits exist, then that number is actually the sum of the infinite geometry series. Okay, so a series that does not converge is called a divergent series. Now there is a very famous theorem which tells you in which case that you can compute the sum of the infinite geometry series. So if the common ratio r have the absolute value less than 1, then the infinite geometry series converges, and we can actually compute the sum in this case. It is given by a1 over 1 minus r. So an intuitive way to think about this result is that you know that's because the absolute value of r is less than 1, then the value of r to the n should be smaller and smaller, and then its approaches 0 as n tend to infinity. Right? So the limit of Rn when n tends to infinity is 0. For that reason, because Sn is equal to a1 times 1 minus r to the n over 1 minus r, then because Rn tends to 0, then in the denominator you only get 1 when n tends to infinity. So Sn should approaches a1 over 1 times 1 over 1 minus r as n tends to infinity. So actually this gives us the desired properties. So we can actually use this to prove the following interesting problems. Well, when we write a real number, we might sometimes be facing the problem that the number might have on the right hand side of the dot infinitely many numbers. Then this is one reason why we care about infinite geometric sum. So the decimal representing a real number actually is an example where you see the appearance of infinite series. So let's take a look at why we can compare 0.99999 equals 1. Okay, where you see that the sequence is actually not terminates. Okay, so 0.999 etc. is actually computed by first take the 0.9 plus 0.09 plus 0.009 plus etc. And 0.9 is actually 9 over 10, and similarly we have 9 over hundreds plus 9 over 1000 plus etc. Well, what is 100? It is 10 square. What is 1000? It is 10 cube. So this becomes actually an infinite geometric series where the first term is 1 over 10, right? Sorry, for the first term is 9 tenths, and the common ratio is 1 over 10. So you see that the common ratio in this case is 1 over 10, which has absolute value less than 1. So you can use the summation result, saying that the sum is actually 9 over 10. It is the first term times 1 over 1 minus r, which is 1 over 10 in this case. And so 1 minus 1 over 10 is nothing but 9 over 10. So what you are doing is dividing 9 over 10 by itself, which is give you 1. Okay, so that is a very interesting way for you to use infinite geometric series in order to show that the repeating decimal 0.9999 is equal 1.